dead battery. That's the reason.
Oh, right. We'll just.
Okay, but let me just go on like this. Does everyone understand me? Yes. Okay. No problem. Today we have a very packed program, but that does mean that it isn't going to be interesting. We have. I'm calling 3 groups of 2 people each time in front, each time on a certain subject. And the first ones are James Smith and Max Ogden, who are going to talk about versions, how to version data online on the web. And yeah, so James Smith, please go ahead.
Okay. Hello. Thank you. I'm James Smith. I'm a developer at the Open Data Institute in London. I'm flopping on Twitter, as you may have heard on the main stage yesterday. I'm going to talk about collaboration. At the moment, how we collaborate with open data is not great. If it was the open source movement, we'd still be stuck in the kind of pre-SourceForge world. And as a developer working on open source software, now we have much, much better ways of doing things, mainly through GitHub. GitHub's kind of changed the way I work as a developer. It's produced this incredibly easy flow of how I can take your code, I can make my changes, and with a couple of button clicks, I can get my stuff merged back into yours. It reduces the barriers to collaboration. And if we could do that for data, we could unlock a whole load of really good effects. This isn't a new idea. People have been talking about doing this for many years. And it gets talked about a lot as Git for data, right? Git isn't necessarily the important part, but that's what gets used. There are some problems with Git, though. So a few people are looking at replacing Git, like Max and Pieter, for different types of data. I think we can probably do more with the tools that we have. I think we can do quite a lot with Git. So I've been spending some time looking at how to improve Git for working with data. So I'm going to show you some of the stuff I've been doing. This is some data, not very much, obviously. And I've made some changes to it, and it's in a Git repository. And you can't tell this is a default view, Git's line oriented, so you can't tell what's changed. This is pretty useful. Fortunately, we can do some things. So it doesn't matter what Git does internally. All we really care about is how it presents those changes to the user. And it's pretty configurable, actually. So Git has this interesting mode called word diff, which says just show me the changes in words in the line, not necessarily the whole line at a time. So that seems quite handy. What's even more handy is we can customize what it thinks words are based on different file types. So if we can say for a CSV, use this other regular expression. So I've started playing around with this. And the first thing I tried was, well, let's just tell it that every single letter is a different word. And this is already a hell of a lot better. Right? This is a good step in the right direction. You can see we've actually added a column now. And there's a row that's been added in the middle. That was completely lost before, and some removals and changes down the bottom. It's not quite right. It doesn't quite line up to the fields. So we can be a little bit cleverer about it and tell it that words are things that don't have commas in, that end with commas. And there we go. We have a decent diff of a CSV file in a Git repository on the command line. And this is great. Everybody using Git has the command line. So this is a good step in the right direction. But not, so you can actually configure your own Git installations with a one-liner to do this. We've made a little script that you can drop into your terminal, and then you can say git diff CSV, my CSV file, and you will see exactly that kind of view, which is really nice. However, not everyone uses Git on the command line, including me, and I'm supposed to be a professional. So it'd be much better if we could use the web tools as well to do the same kind of thing. Unfortunately, GitHub itself isn't open source, so we can't change that, but there is an open source equivalent called GitLab, which we can. So I decided to have a little hack around with this. Displaying, we need to change the way the files, the CSV files are shown, and the way that it shows the diffs. The files are pretty easy, you just show them the table, that's no problem. The diffs are more difficult. You actually have to work out what the diff, what the table really is. But fortunately, just when I was looking at this, along came this. This is QPHX, I think that's how you pronounce it, by Paul Fitzpatrick. And it's a bit of JavaScript you can drop into your browser to do diffs on tables. So I thought, fantastic, that's really good. We can just drop the old file and the new file into the HTML code, call the right bit of JavaScript, and there we go. This is a shot of a CSV diff in GitLab that you can go, you can collaborate on, you can do code review on, as you would in a normal software process, and you can see exactly what's changed. We've got a new column, a new row, and the changes down the bottom corner. This is fantastic. I think this lets us do about 90% of what we need to do with small data sets, certainly. Interestingly, just after we published this on the OGI blog, GitHub released their CSV viewer. It's quite nice. It shows CSV in a nice tabular form like that. You can filter, so you can actually use it to search through large blocks of data. That's really, really good. But they didn't do diffs. So the diffs are still useless. Hopefully sometime soon they will do diffs. And then we'll really start to unlock the power of that collaboration platform for data. Once you've got that, you can start building an ecosystem of services around those sort of data repositories. This is one example of something that we built as well, which is a viewer, a friendly viewer for data that's stored in Git repositories, so you don't have to look at it like it's in Git. You could look at it like it's on a nice data portal. And in future, this is work in progress. I need to sort of carry on looking at how it handles mergers, complicated mergers like the one up there, conflict resolution. Fortunately, QPHX can handle all of this, which is really good. Looking at different dialects of CSVs and so on, and building more tools around that ecosystem. So there's definitely work to be done. You can contribute. This is all open source. We work completely in the open. You can contribute to the GitLab fork or to the command line configurator if you want to. And that's me. I'll hand straight over to Matt to go through the next.
So to wrap up, we've seen a very nice GUI, graphical user interface for using Git with data. But what if Git itself was not perfect for data? It isn't perfect for data. So that is what Max is going to solve. Next up, please.
Hi, I'm Max Ogden. I'm here from Oakland, California. I used to work at Code for America a couple years ago, and when I was there, I was working in a city, and they had a lot of data, and they had it in a city's preferred data format. There's, for instance, in GIS, there's a thing called state plane projection, which is you don't use latitude and longitude, because then every time you have to do something with data that only is relevant to your city, you have to project it into world coordinates. So it's just easier if you just project it into coordinates that's like a box around the state or the country that you're in. So that's great if you work at the city and you're used to that projection, but then if you give it to anybody else, they want latitude and longitude. So that's a form of dissent. Like the city will always want their version of the data, but outside people will always want a different version of the data. And so there is no right answer, there are two right answers, or there are n right answers. So one of the things that I started working on was, okay, if the city publishes the data in their version, and then I want to consume the data but run it through some filters and make it work with my preferences, how would we actually be able to collaborate on this? And what if the data set is really large, and what if the data set is updating all the time, like in plus GPS locations where I get thousands per second? So I started working on a project called Data Couch back in the day, and that's now not a project anymore, but what I realized was that there wasn't any fundamental underlying piece of infrastructure that I could build on that handled all that synchronization and management of the different versions of the data in kind of a way that Git lets you do it. And so I now have a project. I'm working on a 6-month grant to prototype a project called DAT, and DAT stands for data. And all it does is it tracks data and syncs data. It's largely inspired by the CouchDB project, if you've ever used Couch. So my philosophy is that to consume and publish data, regardless of size or frequency, it should be easy. It should be a one-click thing. You should be able to find a data source and say, I want all of the data, and download it, and you get the entire full data set. Or conversely, if you want to publish, you should just be able to take any data source in any format and say, I want to publish this somewhere or host it on a server. As long as you have the hard drive space and the bandwidth, you should be able to host it. There shouldn't be any other technical barriers. And this is how it works today, and I've done all of these many times. A lot of times you'll get bulk downloads, which are great, unless they update. So if you get an FTP access to a large data set, maybe it's a terabyte. If they add a new item tomorrow, it's a terabyte plus 1. So you have to download the whole thing again and then figure out what's changed since yesterday and then merge it yourself. At that point, you have about this much code. On the other end, you have REST APIs, which usually only give you like the last 50 things, and you have to say, get the next page and get the next 50 things, and if there's a million things in the database, then you're doing 10,000 calls or whatever. So there's trade-offs to both of these approaches. You can also, if there aren't bulk downloads or REST APIs, you sometimes have to scrape HTML. So things like ScraperWiki are the only ways to actually get like kind of live data if something changes over time. But with all these, you have to write data import scripts. And I don't have a good term for data import scripts, but we need like a one-word thing for them. But basically, I want to get rid of data import scripts. That's my campaign, is that there should be no more one-off data import scripts. Like Rufus from OKFN has a great graphic somewhere that shows, there's Excel, Microsoft Access, like Microsoft SQL Server, SQL, and then different flavors of SQL, and CSV, and XML. There's all these formats. Then there's like Redis, MySQL, Postgres, and there's all these databases. And what people do is they take one of them on this side, and then they write a one-off script that inserts it into one of them on this side. But they don't work on any other configurations. So there's all these one-off import scripts that nobody gets any value of, and only one person gets value of. And usually they're not shared. They're not open source projects in the proper way. So this is kind of the idea behind DAT, is that it is conversion and transformation, and then when you can convert data from a format and get it into the DAT format, then you can also transform it. So if you can import the data from the SQL server at the city, reproject the coordinates into latitude, longitude, that's both a conversion and a transformation. And then you can host that somewhere and people can sync down a subset, and that's a really important use case for me, is if there's a terabyte of data and you only want the stuff from the last week, you should be able to just get that subset. But if you want the full terabyte, you should be able to download all of that as well. And then it should work for real-time sync as well. So if you don't care about historical data, you don't even care about the last week, you just want everything now, or everything at this point in time forward, or you just want the newest stuff, you just want to get the kind of the Twitter fire hose, it should support that kind of operation as well. And then it's a command line API right now. It's designed to work in a server environment, so you can host it also, and there's a programmatic API. But this is kind of what I have so far, what I'm working on. So you can initialize a project. You can put some data into it just over Unix pipes. It's a command line tool. You can dat-cat, which will print out the full data set as a stream. And then you can actually, this is fun, you can dat-cat back into dat. And all that does is it reads its own data back into itself. Usually you would dat-cat into a transform and then put the transform back into dat, and that's an example of taking all the data, transforming it, and then putting a new version of the data back into the store. And then you can start a server and people can access the data or clone from that server. And then all it does is store things in a .dat folder. So I've stole a lot of good ideas from Git, but I've ignored all the source code specific parts, and I've focused on making the data part fast. So my kind of high-level goals are, I want to not standardize a tabular data format, but rather just make a de facto target format that kind of offers these fast sync capabilities, and these large data set supports capabilities. So a de facto tabular data format. So if you're, after DAT exists, hopefully, if you make the decision that you're going to write an importer for a data set, instead of writing a data set into Postgres importer, you could write a data set into DAT importer and then use an existing DAT to Postgres importer, and you don't have to rewrite half the code. And hopefully, after the ecosystem saturates, there will be all these importers sitting around in a nice package manager, and you won't have to write any code. And then automated install and synchronization of data is kind of the idea. That's how Git works. You can just say git clone, and you get the full history of all the changes of all the code. I kind of want the same thing for data. And then getting rid of the data import scripts. But also some philosophical ideas. I don't want to make DAT a fully featured project. I want it to be the smallest kernel of functionality possible. And I also want it to be fast. And the last two things actually work together. So the transforms are just Unix pipes. They're just standard in, standard out. It's probably going to be a line-separated JSON format. So if you can write a program that reads data and splits on new line, parses a JSON object, does something to that data, and then writes it back to DAT, then you can write a transformer. So you could write a transformer that geocodes. All you do is you take the data, you look at the latitude-longitude column, you go and make a network request to whatever geocoder, you add a latitude-longitude column, you take the address column and then you add a latitude-longitude column. And then you write that back to DAT. And what that does is it handles storing what you did to the data, so it increments revision numbers, and then makes sure anybody that's syncing from you gets the newest version of the data. And then there's an example actually of doing this in R. It's the first R that I've written, so it might not be idiomatic. Well, I guess the internet isn't, but maybe it'll load. But the idea is that while I'm writing that in JavaScript, you don't have to know any JavaScript to actually use it. It should just be as simple as using any other command line API or JSON. And JSON is basically in CSV or in every language. There's a parser for JSON or CSV. So this is the main philosophy. Small pieces loosely joined. And the way the reason I'm using JavaScript, and specifically Node, is because of NPM, which is the Node package modules ecosystem. It's the package manager. There are, I don't know, 40,000 modules now, and each module is just a bit of code with a version number. And then a module can depend on other modules, and what it turns into is something like this. This is actually, this one in the middle, this circle, it represents a Git repo. Every one of these circles is a Git repo. They're also published on NPM as modules. And this is a tree, a dependency tree visualized. So this circle in the middle I started in January, and it's a game engine. It's actually for making kind of Minecraft games. But instead, like if you had Minecraft, it would be a giant circle made by one team. But this is an open source ecosystem, and I made the smallest kernel possible. And then all of the different colors are different authors, and the lines are who depends on what. So everybody depends on my central module in this inner ring, but then people have written other plugins. So if you wanted to make terrain, there's terrain modules. If you want to make trees show up, if you wanted to do physics for the player, or make that like monsters show up and attack you, there's all these different plugins for the game. And some of them get really abstract. So some of them are just things like physics has nothing to do with Minecraft, but you need physics for Minecraft. So out here you have things like keyboard bindings and things that aren't directly related. So this ecosystem, none of these modules existed. There's, I think in this one there's 100 dots or so, or maybe not all of them are visualized, but none of these existed in January. In the last, I think 9 or 10 months. All of these have kind of sprung up because of tools like GitHub and tools like NPM that let people rely on each other's code without having to have central coordination. So I want to keep doing it. So and build on that success with that. So outside the scope of that, I don't actually want to enforce a diffing or merging strategy because there is no canonical, agreed upon way to diff or merge data. It depends on the use case. So instead, I'll just give you hooks that you can build your own diffing and merging logic on top. I don't want to do complex queries or index. I'm not going to support SQL queries or anything like that. You can build that on top. I actually just view dat as kind of a proxy. So if there's a bunch of data externally and you have your favorite database internally, instead of trying to write an importer from the external data to your favorite database, you just let dat sync all the data, and then you can tell dat, make a Postgres database for me from the last week's worth of data or from the entire data set, or kind of, I guess, there's words in data like facets. You could use dat to create a facet or a window to the remote data store. So you tell dat, make sure the data is updated from the remote source, but then every time it gets updated, make sure Postgres is also updated. And then end user applications, dat is for developers, but I think we could build things with dat, given its features that people could actually use. I also don't want it to be a package manager, so when you publish a data set, whenever we figure out how to do that, I'd love to reuse things like GitHub or databases that are already hosted. Anyway, I'm trying to get the point across that I don't want more features, I want less features in dat, but because of that, all the features are up to third-party developers to implement. And so my main use case is not small data, basically. So small data is awesome. Most data is small data. Well, I guess not if you look at lines of data, but number of data sets. So if you can put it on GitHub, put it on GitHub. That's the simplest possible thing. If you can email it, put it on Dropbox, put it on an FTP folder. If it doesn't update that much, if it's easy data, small data, then use easy and simple tools. But there are things that don't work with things like Git or like emailing attachments around. So large scientific and research data sets, things that update a lot. Big data, I hate that term, but it is what it is. Or streaming or real-time data. Those are kind of what I'm targeting. And my initial goal is make my beta testers happy, get them to actually use it, and make it fast, and then get the ecosystem established. So some of my beta testers, so I wrote a README on GitHub before I had any code, and it had a graphic, and a lot of people read it, which I was very surprised about because it was like vaporware at that point. And a lot of people emailed me and they said, hey, I'm at this organization and we want this, but we don't want to build it ourselves because we know we won't do it in the right way. So now I'm kind of my grant money is like funding me to be this like consultant almost for all these different organizations. And some of the organizations are the company If This Then That, which handles basically synchronizing between different web platforms to let people do things like if I tweet a photo, email it to myself for an archive or things like that. Another company is called Firebase, and they are like a hosted backend for apps that deal with a lot of data sync. There's JPL NASA, who has a lot of different large like telemetry data sets between departments that they have no way of collaborating on because it's all, they always have to write these one-off importer scripts to work with each other's data. So my initial beta testers, I'm looking for more, so if your organization might be interested in dealing with large data set sync between formats, please go to the GitHub repository and leave your use case in an issue, but I want to make the beta testers happy and make it an actually viable thing and get them to have some agency in it so that they become, open source is built by people working at companies. So the background is that it's a 6-month window. Yeah.
30 seconds to wrap up.
Oh yeah, totally. I'm almost on the last slide. For the background, I have 6 months. It's 100% open source, and the repository is just called DAT under my GitHub. And you can contribute through many different ways, and there's code in there, and there's benchmarks, and play with it if you're a developer. And so far what I have is to add a 52 million line CSV takes 13.5 minutes. To add it with DAT takes 11 minutes. So Git and DAT are about the same for importing. But then to change one line, if you just add a new line, 55 million and one lines, then it takes 8.5 minutes for Git, but it takes 5 milliseconds for DAT. So kind of the real-time data use case really shows off there. So I'm hoping that you guys will get involved, and thank you very much. Woo.
If there are questions for James and Max, please ask them afterwards. I'm very sorry.
No, it's all good.
And I would like to call Kamila, Markram, and Karthik Ram to the stage, who are going to talk about open science and everything related to it, or the data problems that we currently have in open science and how we might fix them.
Hello everybody, thanks for having me here. I'm Kamila Markram, I'm co-founder and CEO of Frontiers. And what I'm going to be presenting today is how we at Frontiers disseminate and popularize science. So for those of us who don't know us yet, we are a community-driven, open access academic publisher, and we are as well a social network for scientists and researchers and basically everybody who's interested in science, academia. So some facts, we were founded about 6 years ago at the EPFL, and that's where we're still headquartered in Lausanne, just around the corner. And very recently this year we joined the Nature Publishing Group. Some numbers about us, so we're publishing academic journals across 18 academic fields right now, such as neuroscience, physics, bioengineering, covering more than 250 specialty sections. We have around 30,000 scientists serving on the editorial boards of Frontiers, and those are really top-notch scientists, so they're in the 1 or 5% of scientists worldwide. We recently reached the 100,000 users mark, published more than 14,000 academic articles online that had about 25 million views. So this just a little bit as a background in Frontiers. So when I present Frontiers, I really like to point out that it really is an IT platform for open science and for innovation, where people can come in. Currently it is us, but others will be joining in as well. We're opening up that platform. And really what it right now compromises is two aspects. One is the publishing aspect, and the other one is the community aspect. So when it comes to the publishing platform, we're obviously open access, so that means that all content on Frontiers is freely available to anybody. But when we set out and founded Frontiers 6 years ago, we really wanted to change publishing and solve the many problems that exist in traditional publishing. So we have a very different peer review system from any other publisher out there. We use online impact metrics to evaluate research articles, science, and scientists. And we use these impact metrics as well to highlight really the best research and popularize it for scientists, but as well for the public. So the community platform is really about providing online tools for researchers and anybody really interested in academia. And that means that we have built a social network, which is called Frontiers Research Network, where you can find profiles of academics, but as well all kinds of multimedia stuff and services such as video lectures of scientists, or people organize conferences and events on the platform, and you can follow these kinds of things. So our mission is, so we're really community rooted. That means that we work with scientists, we're scientists ourselves, and that's really where we see our foundation. But our mission is really to democratize publishing, to disseminate science, and to popularize science. And it's particularly those two that I'll have briefly the time in 5 minutes to talk about. So when an article is published, an academic article, the output of research is published on Frontiers, it's obviously open access, which means that it can be accessed from anywhere in the world for free and downloaded for free, and there are XMLs attached to it as well, so people can download even the data sets around that. And this is great for readers, but it's also great for scientists and the authors themselves, because it increases views and downloads and citations of these articles, which is something that scientific careers are partly built on. So open access is really great in increasing accessibility, visibility to these articles, but that's not all. We're trying to find ways of how to disseminate and push these articles out even more. So we're investing quite a lot of efforts into social networking. So obviously we have pages on Facebook, Google+, Twitter, LinkedIn, and so forth. And whenever a great article is published, it gets pushed through these channels to broader audiences as well. But we have as well built our own network, because we see that Facebook and even Twitter are not really specific enough, not really catering enough towards the needs of scientists. So this is what the Frontiers Research Network does, and this is what it looks like. So anybody on Frontiers, so those 100,000 users, the 30,000 top-notch editors that you've seen, any one of them can have an academic profile where they showcase their academic achievements. These are their publications, which is what research is basically made of. But it's as well as other things that give a more realistic picture of the scientists. So for example, there are video lectures, but there are as well blogs, news, research topics that they organize. And it all basically comes down together in this little activity stream where you can stay up to date with what a researcher is doing. So it's actually a great way to stay up to date for students as well, looking for a mentor or for a lab and finding out about the people that they would like to collaborate with or work for. So then you can follow any type of scientist basically just by a click button, and it then comes together for you in this activity stream where you can stay up to date with publications, but as well as conferences that are being organized, news, and so forth. And this is via the people that you're following, but you can as well obviously follow concepts. So for example, if you're interested in schizophrenia or autism research or nanoparticles or whatever, you can follow these types of concepts, not necessarily knowing who are all the people working in these fields, and it will come together for you in this activity stream. So you'll get the latest publications about these concepts, as well as news around that. Conferences as well that are being organized. You won't believe it, but in academia, for example, there's not a proper events calendar for certain topics. So Frontiers really is the first and only platform that combines open access publishing with research networking, and we think that this is really quite a good distribution system to increase the visibility and the impact of the scientific articles, of the science itself, but as well the people who make the science, who are behind the science. And just very briefly to show you how we popularize science. So one of our big missions is to laymanize, so to say, make it more accessible, the science that people are writing. So So believe it or not, but today science is so very specialized, the methods are so very specialized that one scientist doesn't really know what a neighboring one in a neighboring field is actually doing. So we developed a system which we call Turing, which I'm not going to go into how exactly it works, but basically we use online metrics to highlight the very best research, and people are then invited to write these articles in a way that it's accessible to other scientists in the field, but as well to the public eventually. And another project that we are just about to launch in November at the Society for Neuroscience is Frontiers Kids. So this is a journal based on real discoveries, real original research, but edited and reviewed by kids. So scientists actually have to pass that type of filter of the kids saying, and they're really tough. So we had already the first round of reviews where kids will be saying, okay, I understand that, or I don't think that makes sense. And then it will be published in that kids journal, basically. So I think those are my 5 minutes. Thank you very much.
My name is Karthik. I am an ecologist at Berkeley, and I've spent most of my career working in the field, taking lab notes that look like this. I'm actually lying, my notes are not that disorganized, or I don't actually have any artistic skills. But other biologists have been doing this for well over 200 years. A lot of this data is now sitting in museums, and all of the specimens they collected have also been sitting in museums. These data have been digitized, and now they're really accessible to a lot of web platforms. But now we're spending a lot more time collecting real-time data. We're collecting sensor data from things that are out in the ocean, things that are out in forests, and satellites are picking up real-time weather data, real-time changes in vegetation all across the planet. And so we're actually now drowning in a ton of data, but all of the data that we use to come up with the knowledge that we generate are actually not easily accessible. So people don't share their data, so it's very hard to validate findings or produce findings. But this problem is actually quite pervasive even within research groups. If you don't document your data and disseminate your data, somebody coming into that group over a certain period of time is just going to look at all these results and go, holy shit, I have no idea how you got them. And so it's really a big problem when a lot of the analysis pipelines and the raw data that are used to support these conclusions are just now black boxes. And they're described in very, very short sentences within papers, and there's no supplementary material to go with it. And so a lot of the research findings that you read about, you just sort of have to take them at face value and trust that everything's been done right. If you like to build upon it or reuse that a little bit of analysis or a little bit of code to do something else, you really can't do that. And so we have this huge problem where science is closed. We are incentivized to work in little silos, not really collaborate outside of our immediate research groups. And so, as a result, a lot of the data that we collect just ends up being recycled in the backloading dock when the computer dies and it's no longer fast enough. And even if you've deposited the data somewhere in some hard drive without any metadata, it's quite useless. And collecting data is expensive, especially if any of you have been out in the field for 6 months when you're cold and wet, and you realize that the data you collect is really, really valuable. And so a lot of us within science have been pushing for open science. It's really not such a common thing, but there have been a fairly growing subset of people involved in this. Open science can mean different things to different people. It can mean something as simple as open access publishing that we just heard about. And at the other extreme, it can mean people that are very, very proactive about sharing the things that they do every day. They maintain lab notebooks. You can actually see all of their code, all of their data, and all of their thinking process as they work through a research problem. And so it's easy to see the benefits of open science, but it truly comes together when people doing different things can support each other. So for example, I'm actually both theoretical ecologist and a field ecologist. And And so when I develop models, it's really, really hard to build good models without good data to test your models against. And so one of the things I've been working on this past year is trying to look for very messy data on insect population dynamics, and these data have been collected for well over 20 years. People love insects. They just sort of collect and count insects. And believe it or not, it's impossible to get the raw data. The best thing I got was somebody that faxed me an old data sheet, but they couldn't actually recall what they did or what species they even studied. They just had to look at the species code, and they just looked at that and went, okay. So I spent a year just running these experiments all over again when I didn't need to. And then there's people out in the field that are trying to solve both very fundamental problems, but also applied problems that are dealing with invasive species or trying to save some endangered species. And when you have limited resources to collect data, you want to collect the data that best fits the models that will give you an answer. You don't want to collect everything. And so having access to good models and good code really helps you narrow down your data collection efforts. So collectively, we want to be on the top right quadrant. We can actually push research really fast, really forward, if we can share our code, share our methods, and also share all of the broad data that are being used to inform these models. And so, well, now we have the incentive problem. People who do this really have to believe in the power of open science. But at least now the incentive structures are changing a little bit. A lot of studies have started to pick up the fact that people who share their data are more likely to get cited, your work has become a lot more visible. It's really not something that's immediately measurable, but it's an effect that people like me are seeing. When I share my data, I usually never have people speak me. It always leads to collaboration. And if you're funded by, say, the National Science Foundation or another funding body, they're also starting to recognize that these other products that you produce, not just that one final paper that comes out of a research effort, it's the data, it's the code, it's anything else that you produced along the way, can be used for reporting purposes as something useful that you built. And so, how does this all fit in with R, which is what I'm here to talk about? R is one of the many tools in the ecosystem of open science that can really facilitate this process. There are many, many scientists that use R just for one thing in their full analytical workflow. They use it just to analyze their data. But R can do a lot more. It's taken a very long time to move scientists away from using GUI tools. This is what they showed me when I first started my PhD. And if you look for help, the only thing you'll find are screenshots. It's really not a reproducible workflow. You can boil this exact same thing down into one line of code, and this line of code will make sense to any statistician who's looking at your analysis or looking at your supplementary material. And this type of workflow is really, really powerful. It's reproducible. Someone else can build upon it. Someone can verify it. And if they have access to the data underneath, they can reproduce your entire paper. And if you're trying to do open science in any environment, including R, you need tools. And the number of tools in R have been growing exponentially. This slide is a couple of years old, and it actually shows that there's about 2,000 R packages. At that time, we actually have more than 5,000 if you count the packages that are in the official repositories, but also on places like GitHub. So anything you could possibly want to do in R, there's a tool for that before you start coding. And if you'd like other traditional incentives for writing R code, you can actually publish them in a lot of domain journals. Because I'm an ecologist, I'm showing the ecology example, but this is very, very common across different domains. And so a group of us, we actually first met on Twitter 2 years ago, after talking about open science and building tools for open science. We ended up forming an organization called rOpenSci, rOpenSci for short. Our mission is to build tools that enable programmatic access to data so we can complete the entire pipeline, not just the analysis part, but also the data acquisition part. And a few months ago, the Sloan Foundation decided to fund us, and now I'm working on this full time, building tools within my domain, but also helping scientists in other domains build similar tools that can leverage open data. And so we've got about 50 tools so far. We're building a lot more, but they roughly fall into things that can go after data, things that can go after journals that have full open APIs, and things that let you share your own data. And so since this is a 5-minute talk, I'm just going to give you a little taste of the kinds of packages we build. For the Public Library of Science, for example, the flagship open access journal, they've opened up a complete API to every part of their journal. The titles, abstract, figures, everything. And so we have lowered the barrier through R with just one single package, a few functions. You can pretty much grab any queries you can run and pull up trends. So for example, this one line of code pulls out how often reproducible science has been mentioned in PLOS in the last 10 years. Dryad is a repository that backs over 196 journals across a bunch of different domains. They're always adding more journals. A lot of high-impact journals now require you to share your data when you publish an article. And again, with just any kind of identifier, in this case a Dryad identifier, we can go grab all of the data behind the research article. If there are any evolutionary biologists in this room, we've got tools that can go to Treebase and grab published phylogenetic trees. Again, in this case, with just a quick search in the author and just the first hit that came about. And that line of code pulled out the entire first figure from our paper. And for people that are interested in conservation, we can pull out distribution records across multiple repositories and quickly plot them as well. So here's a distribution of pumas across North America. And then there's other data we can leverage to bear on these other types of data sets. For example, I just showed you distribution records for one species. R is a vectorized analysis tool, which means you can just work on tens of thousands of species in just the same line of code. And using other portals like the World Bank Climate Portal, we can actually pull up either past projections or future projections for any basin in the world. And so you can take these data and then use them to explain the distribution records that you're seeing and actually do any kind of niche modeling if you're interested in that. So we like to dog food our own tools. The tools that we build are usually around the biological sciences, but we're actually expanding out and looking for collaborators in other fields. So an example of these other kinds of tools are,
Sorry to interrupt, 30 seconds.
okay, are tools like altmetrics that grab the impact of your research. Again, it's a vectorized tool, so you can actually pull data on hundreds of papers if we need to at one time. And so the whole idea is not just consuming data, we're also about depositing data, so we have tools that can take your data, add metadata to it, and then deposit that in places like Figshare, which is a platform for sharing your data, but it can be anything from your institutional repository. So ultimately, the goal we want is for people to complete the full analysis pipeline, so we can reproduce the entire paper. We want it to be an executable paper. And so GitHub is great for that. If your data are small, we can deposit data along with your code and along with your manuscript. And it's easy just to collaborate on the whole writing process. I do not write papers in Microsoft Word anymore. I don't email documents around anymore. And you can actually see the entire process by which the paper is being written, who added data when, who added code when, who added the figures, who wrote the actual text. You probably even figure out authorship contributions this way. R fits in very nicely in this process. We can embed R code within these documents, make the whole process very literate. And anybody that can do a git clone on a repo can probably pull the data down, the R code down, the R packages, and just read on the whole thing and either build upon it or just verify the results. So if you go on GitHub, you can see a lot of manuscripts. This is R code being run. The Markdown is rendered on GitHub. And so we have a whole ecosystem of tools that can make open science possible. We're working in one of those, which is R. And so if you're working in a different domain with R, we'd love to hear from you. We are rOpenSci.org and rOpenSci on pretty much every other platform.
While we welcome Nicholas and Steven to the stage, I would just like to reference like in two calls for action. Yes, please inform. That if you want to connect to your social, if you want to make science social, please join Frontiers. If you would like to reuse tools, or please reuse tools for science. If you have different domains than Karthik, please reuse these tools. They are great. And I think we have a third call for action concerning open science.
Yeah. So maybe just there is not enough time to put everything in this slot. So I will have one presentation of our project from Berkeley. So I'm Pieter from Berkeley. We are doing a project called Free Library, which is an annotation platform for open access papers. So the idea is that you can collaboratively annotate papers, share them with others, share annotations and so on. And everything is in the browser, no installations necessary. So it will be a free today at Hackspace. So the Hackspace down there. So everybody is invited to come and see the presentation of our project.
I know, sorry that we're going 10 minutes over time, but I'm sure you will forgive us because these two last talks are going to be great. So please, Nicolas Balde.
Okay, thank you. I'm Nicolas Balde, founder of a project called Open Meteor Data. So weather is everywhere. Most activities are impacted by weather. It's very huge. 25 to 35% of European countries' gross product is sensitive to weather. And many activities are impacted. 90% of cost losses are due to weather. So there is a lot of things to do, a lot of opportunities for making startups or things. And it's working quite good because in the US, there is a big industry linked to weather, growing at a 20% rate per year. But in the Europe, it's only growing at a 2% rate. And why? It's not because the European market is already saturated. It's just because data is not free. Only few countries are sharing weather data. The best one is the US. They are doing this for decades. Norway is quite good too. They are sharing a lot of things. Canada, Netherlands, and most recently Finland. Here are missing some countries we think are doing open data, like Switzerland and the UK. They are not here because they have not a full open data policy for weather. They are sharing some data, but the most important data sets are not free. You have to pay for hundreds of thousands of euros getting this, like model forecasts or things like this. And there is also a few countries with some regressive steps toward open data. Spain has been open 1 year ago, and they closed everything because of a ministry thing. And Hungary ministry was drafting a bill 1 year ago saying that weather is only a state problem and no private companies should be involved. So it's not a good step for open data. International regulation says data should be shared, but it should be accessible for free for research. But when you look closer, it's not so easy. It's not so easy. For example, Météo France, our national institute, say, okay, we are delivering data for free for research. But if you look closer at the small lines, the license says if your research will lead to a patent or a license, you cannot get the data for free. So, what's the link between all those political problems? Because data will be open soon, but there is a global movement onto this. The G8 signed the charter in this way last June, but there is a lot of political problems in getting this data open because it needs to change both national and international laws. So it will take some time. So what's the link between those political, official things and hackers, Fab Labs, mobile apps developers? So I'm a paraglider pilot. If I want to stay alive, I need to have a good understanding of weather. And I felt very disappointed because I could not find any website with useful information for paragliding. So I'm a geek and say, I cannot find one, I will make one myself. So I'm young, I've been asking on National Weather Service, hey, you got the data I need, could you give it to me so I can do my website? And I was disappointed because my mom and dad were not, saying it was not okay to sell the house for being 1 year of forecast. So I said, okay, I will do it by myself. I found quite big computer, drawing 4 kilowatts of energy, and I put it in my bedroom. So, mom and dad were very happy. Of course, no more need for selling the house, and free eating. Thanks to this, and a lot of Googling, I finally got forecast from my paragliding. Wow! It was 1 year of work. And then I said, maybe I'm not the only one needing those kind of data. Maybe not every mobile app developers can do this kind of work. So, since this data is not available, let's create an open project sharing this data for everybody. So it was the birth of Open Meteor Data. We aim to making meteorological data available to everyone, and it gets a lot of support from the initial paragliding community. So now computers are no more in my bedroom, it's in a real data center. The project evolved with the idea becoming a home for every project around weather, becoming a kind of OpenStreetMap, but for weather. There is a lot of challenges with open meteorology. First one, forecasts. So I'm kind of solution. Another one is stations network. A lot of people got their own stations at home. Some are trying to get her in the network, but most of the time there is a lot of small problems, like stations are not in the right places. Sensors are misused, for example, wind sensor behind trees. We never know what kind of data we have, and data is closed. There is no licensing, and most of the time they say you cannot use this data for commercial use. So there is a huge opportunity creating an open network with a special focus on data accuracy and classification of different levels of quality.
30 seconds.
Okay. We also need to design a clever and cheap sensor based on Arduino community and things like this. And there is a lot of sources for data, so someone not meteorologist don't know where to go. So create a portal, a search engine, everyone can submit link to data sets. So it's quite easy to find everything. We need software because meteor software are usually very difficult to compile or very old-fashioned, so we need to make them ready to use, and most of important, we need a knowledge base, because we want people without meteorology training being involved in weather. So we need to explain what data to use, how to use it. So I'm quite optimistic because we've seen Linux, Wikipedia, OpenStreetMap, and soon Open Meteor Data. Thank you.
I want to stress that it's funny that he says that it's for paragliding, but in fact one of the biggest discussions today is about weather data. It's of course global warming. And if this data is not fed by open data, I think we have a very bad discussion. So you're solving the world, or you're actually saving the world with this little project, I think. So anyone who wants to help Nicolas with this challenge, please contact him afterwards. Now we have a last short talk by Stephen Flower.
Hi everybody, I'm Stephen Flower. I'm based in Manchester in England. I'm very active in Open Data Manchester. None of that is relevant to what I'm talking about. Well, in the program on Bill Anderson, so Bill's ill, so I'm going to keep this short. I want to talk to you about a project I'm working on. As we cycle through, here we go. So, an initiative called the International Aid Transparency Initiative. It's been going for 5 years now, and it's all around making aid more effective, so overseas aid projects, etc. Part of IATI is the IATI standard, which is what I spend my time on. And this is a data standard to help organisations that are going to publish their information about their overseas aid to describe it in the same way. So the World Bank will describe their activities in the same way as the Global Fund and small NGOs, etc. So when I first started on IATI 2 years ago, there were only 5 or 6 organisations actively publishing data to IATI. And now there are around 180, there are 180 around. So it's growing quite quickly. More and more organisations every day are publishing data to IATI. The model of IATI is that organisations publish on their own websites, or their own systems, XML files, and within the XML files is the data around their overseas aid. And the core aspect to IATI, as you can see here, is a list of organisations on the C can to point to all the files. And each organisation publishes files that contain what we call activities. And every activity, so this is the Department of International Development, every file, so there's a file for North Africa, and within the file there are activities. This one's got 14, this one's 75, this one's got 538. So it's great, there's a data standard, everyone's publishing to the data standard, but after 2 years the data is starting to get a little bit overwhelming, dare I say. Where can I find that project about water sanitation in Malawi, for example? Who else is working on HIV and AIDS in Zimbabwe, for example? So, to stress, IATI is a data standard. Organisations are actively publishing to that data standard, and we've got lots of data. So, just to show you, here's a typical file from the Department for Education. It's got all these activities in, and within that activity we talk about when is it, where is it, how much money is being transferred from partners to others, what are the outcomes, conditions, etc. So the standard really helps organisations to describe their overseas aid and for us to compare and put them together. Now, these activities are really key to IATI. If you can imagine, you pull down an XML file from DIFID, for example, it's got all those activities, but how can I pull down other activity, other files, and start to understand where are those sanitation projects? And this is the difficulty we find. We've got API access, we've got tools around that people are building in the ecosystem, but the core thing is we get calls from researchers, academics, journalists, civic society organisations who just want to get the data. They know there's an API, but they actually want to try and do this. So the thing I just wanted to mention today that we've got, and so if you go back to the registry, if you do a search on the metadata for show me all the files that are about Zimbabwe, you may miss some because they're in different files in different places. So we find in the metadata recorded on the file level isn't relevant sometimes to the activities within each file. Okay. So the thing I wanted to flag up today is what we've just been building with the OKF is the IATI data store. So this takes every night the data from all those files, pulls it down, and then parses out each activity into a database. And that then makes it a lot easier for me, for you, for the journalists, for others, to start to query, give me all those water sanitation projects in Zimbabwe, for example. It sounds a little bit of a regressive step, but we've got a great system, it's dispersed, it's using metadata. Why are we pulling all the data down into a database to redo what's already been done? But I think what we're finding is that it's now we're getting towards front end where I can pinpoint, give me all the projects around to repeat water sanitation in Malawi, or water sanitation and HIV and AIDS from different organisations. So it's kind of putting facets on data that's already to a standard and giving people nice ways to find it. So the IATI data store is in effect launched today. I need a ribbon cutting thing from some pictures. But we'd welcome you to have a look, have a go, give us feedback around this, because we think it's a really interesting step from 5 years on into a data standard with lots of data. Now thinking about what are the effective ways for people to get data. So just to show you the obligatory JSON file that you can get on those activities, and perhaps my control skills are lacking. But also, I think what's really important is that somebody can quite easily call and get a spreadsheet back of those activities that are water sanitation in the lab, for example. And that's I think the bit that's the really interesting part of this. The data system, the data standard is there, but that's what people want. That's what people ask us for all the time. Can you just get a spreadsheet that I can use? So I'm through nearly. There's a Google Doc. We'd love you to collaborate around the data store and gives you thoughts and opinions around it. And of course, everything as well is on GitHub for you to raise issues with as well. But that's it really. I just wanted to share that journey of from the data standard, lots of data, and there are tools we think is quite useful to pinpoint within that massive data.